And then they come and show you some data which agrees or doesn't agree with those predictions. My feeling is that it's useful to know a little bit about the data beforehand, to see the landscape, so you know what it is that these theories are trying to predict, rather than have a theory predict something and show you a kind of random piece of data that fits it. So I'm going to give an introduction to what nuclei look like. I don't mean look like, but I mean what their spectra look like, and a little bit about their structure, and then introduce some simple models. Most of this will be tomorrow, and this will mostly be today, but we'll see how it goes, okay? And remember, I encourage questions. So this is an overview that applies not only to nuclear physics, but to many areas of modern science. There are two ways of looking at many-body systems. One is a microscopic approach, where you look at the individual constituents and their interactions. And in nuclei, that means what is the force that binds nuclei, and why do nuclei do what they do, okay? This is actually the subject matter of most of the Talent courses so far, and it's a very important approach. A complementary approach is a macroscopic one. This should be femtoscopic, I guess. A macroscopic one where we look at the many-body system as a whole. We look at the nucleus as a whole with a shape, with vibrations, rotations, and excitations, and we try to assign quantum numbers and predictions for the system as a whole. And these nuclei exhibit remarkably simple patterns. We try to understand what those patterns are and what is their origin, okay? So this is more a question of what nuclei do, and this is more a question of why nuclei do, but those labels are a little bit fuzzy because both sides do both. Okay, so these are the two perspectives you can use to look at nuclei. I will focus mostly on this, but you will get plenty of this as well during the course. Okay? This is the plan for today and tomorrow. I want to talk about three key ingredients for understanding nuclei. These are very simple ingredients. I want to give a brief introduction to a couple of idealized models. Now this brief introduction will be like one slide for each, and the only reason for that is to give you the names, a few pieces of jargon, so that when I discuss the data, the empirical behavior of nuclei, I can attach some labels to that behavior. But I won't go in any detail here about these models. Instead, I will come back to them after I've shown you the data, and then go into those models in some detail. Okay, key concepts. These are the three key ingredients for understanding nuclei. Now, it's not everything, but this gives you a good start. One is that the nuclear force is short range and attractive. That is, nucleons, protons, and neutrons interact with each other when they're close to each other. Now, that's a very hand-wavy way of saying it, but it has the basic idea behind it. The Pauli principle is the second, which has two aspects. It controls the occupation of these nucleons in specific orbits, and it implies anti-symmetrization of the wave functions, and that has a big impact on residual interactions, and as you will see, is the reason basically why even nuclei have 0+ ground states. And then two-state mixing, or mixing in general. When we do a calculation of any aspect of nuclear structure, we start with some set of basis states. And we have a Hamiltonian. That Hamiltonian invariably mixes those basis states. And what comes out is a result of that mixing. It's the origin of collectivity, coherence in the wave functions. And the simplest one is two-state mixing. And I'm going to go in some great detail on two-state mixing because it's the basis for multi-state mixing. And in fact, very often if you do a multi-state mixing calculation, you can decompose it into approximately a sequence of two-state calculations. And so I'll go through some formalism for this. And this afternoon there'll be some exercises on this. Okay. So I said that the nuclear force is short range and attractive. How do we know that? Well, there's a lot of data that tells us that. But one piece of data is nuclear masses, which very simply give a clue to the range of the nucleon force. You will see this slide 3 times today and tomorrow with different aspects of what these masses tell us. But the total binding energy, or total mass of a nucleus, is the sum of all the interactions of all the nucleons in the nucleus. Mass differences are differences of masses between neighboring nuclei. Those are the same as separation energies. They can give evidence about shell structure, phase transitions. We'll come to that later, and this will also come to later. Now, if you talk about the total mass of a nucleus, each proton and neutron has a mass of approximately a GeV. That means a typical heavy nucleus has a mass of 150, 200 GeV. And excitation energies in even nuclei are on the order of an MeV. So it's pretty hard to learn much about that by looking at the total mass. One always looks at some function of the mass. And one is the binding energy, that is the sum of the energy required to remove each of the nucleons to infinity. And often the binding energy divided by the number of nucleons, the average binding energy per nucleon. So I want to look at that and show you a very simple plot, and we'll see that this immediately tells us that the nuclear force is short range. So this is about the simplest data you can imagine. It's a plot you've all seen. It's in almost every textbook. It shows the binding energy of a nucleus per nucleon divided by the number of nucleons. And it starts off, and the scale here is MeV, and this is 0, and that's 10 MeV. And so it starts off and it increases here, and then somewhere around in the region from oxygen to cadmium, it kind of flattens out. And basically, in first order, it's flat after that. There's a small drop, but we can approximate this as something going up and then flat. And I want to try to understand that and understand what it tells us. Okay? So I want to look at the simplest possible model you could imagine, which is clearly wrong. I like to look at wrong models because they often contain some essence of the real situation. So I'm going to assume that every nucleon interacts with n others, and we will look at different values for n. And all those interactions are equal. And you know that's not right, but we'll do it anyway. And we're going to look at the resulting binding as a function of n and mass. And we'll compare with this binding energy for a plot. Okay, so this is complicated looking, but it's actually very simple. A column is for the case of each nucleon interacting with a certain number of others. So this column corresponds to each nucleon interacting with 2 others. And I do that for a case of total nucleons 3, 4, 5, 6, and 8. Okay, I don't know what happened to 7. Okay. So if you have 3 nucleons and they interact with 2 others, this one will interact with this and this one with this and this, and this one with this and this. Total of 3 interactions. And if I now divide by the number of nucleons, I get the number of interactions per nucleon is 1. If I go to 4 nucleons, each one interacts with 2 others. I have a total of 4 interactions. So the number of interactions per nucleon is 1. 5, I get 1, 1, 1, 1, 1, 1. So if this were the case in nuclei, the binding energy per nucleon would just simply be 1. It would be this line here. So this is what you would get for the binding energy per nucleon if each nucleon interacted with only 2 others. Suppose each nucleon interacts with 3 others. Well, here there aren't 3 others to interact with, so that's the same. Here, this nucleon will interact with this one, and this one. And similarly, you count the number of interactions, 1, 2, 3, 4, 5, 6. There's 6 interactions, 4 nucleons. So the total number of interactions per nucleon is 1.5. If I go to the next one, you can do it, you can work it out yourself. It's 1.4, then 1.5, then 1.5. If I plot those as a function of A, I get a line that comes up like this and then goes off constant, approximately constant at 1.5. If I go to 5 interactions per nucleon, I'm not going to do the counting and things like this, but here it's obviously 1 by definition because there are only 2 others. Here it's 1.5 because there are only 3 others. Here, if you count the number of interactions, you get 2 interactions per nucleon. The binding energy per nucleon is 2. here it's 2.5, here it's 2.5. And so you would get a curve that would go up like this and then be flat. And I wonder now whether I have a mistake here with 8 and 7, but it doesn't matter, you get the idea. If each nucleon can interact with all others, then every nucleon interacts with A minus 1 others, and they're A nucleons, so you have A times A minus 1 over 2 interactions. And if you divide by A, the number of interactions per nucleon, you get A minus 1 over 2, which is this line here. Okay, so you can already see from this very trivial way of looking at it that you have a curve, this curve here, where each nucleon interacts with all the others, doesn't look like this plot. It does look like the beginning of the plot. This curve where the binding energy per nucleon is constant doesn't look like this plot, but it does look like this part. Okay? And so what you see is that you can get a curve that resembles the data if you assume that each nucleon interacts with 8 or 10 others. Then the binding energy per nucleon would go up and then become flat. And so from this very simple counting scheme, which is hugely oversimplified, you can conclude that each nucleon interacts with 10 or so others. 10 could be 5, it could be 20, but that ballpark. Which means that the nuclear force is short range, and it's shorter in range than the size of heavy nuclei. Okay? So from the just measuring the masses of nuclei, putting them on a scale basically, we can already tell that the nuclear force is short range. And it's obviously attractive, or we wouldn't be around to ask the question. Okay, now two-state mixing. There's going to be some heavy formulas here. You will have these slides, so I won't go through every detail of the derivations. And anyway, you've probably all seen this. I want to present it in a slightly different way, which gives you some universal functions. Okay, so here's the problem we want to solve. I have two levels called E1 and E2 with Arabic subscripts, and they have an unperturbed energy spacing delta E unperturbed. They have unperturbed wave functions phi 1 and phi 2. Okay, now I assume that they interact with some interaction V. Okay, and what happens? You know that levels that interact repel each other, and so they will be further apart after mixing than before. And the amount they push each other apart I define as delta ES, S stands for shift. And the final energies are given by E1 with a Roman subscript and E2, and the final wave functions by psi 1 and psi 2. Okay, I want to define the quantity because this is really the key to everything. R, which is the unperturbed energy spacing divided by the interaction. And you will see that everything can be written in terms of R. So you all know the solution to this. I mean, this is really elementary. That the final two energies are given by 1/2 the sum of the initial energies plus or minus 1/2 the square root of the difference in those initial energies squared plus 4 times the matrix element squared. And I can take out, the E2 minus E1 is the unperturbed energy difference. So I can pull that out and I get, this is the same, I get plus or minus delta E unperturbed over 2, 1 minus 4v squared over delta E mu squared. All I've done is just take this out of the square root out here and call it delta E mu. And now using R, I can write this as the same thing. This is the same square root of 1 plus 4 over R squared. Okay? The perturbed energy separation, that is E2 minus E1, is then given by, so I'm just going to take this and take the difference E2 minus E1 using the plus sign in one case and the minus sign in another. I get that it's the unperturbed energy separation times the square root of 1 plus 4 over R squared. And now if I write the perturbed energy difference in units of the initial one, is this getting faint already? Okay. If I write the perturbed energy difference in units of the unperturbed, I get this, that the perturbed energy separation in units of the unperturbed is just the square root of 1 over 4R squared. Okay, go through the rest of this if you want. So this is a universal expression for the final energies in units of the initial energies, and it only depends on this one quantity r squared. Okay, and it doesn't matter whether the initial levels are separated by 3 electron volts or 22 GeV, or whether the interaction is a kilovolt or an MeV. You can always write it in terms of R. The only case where this doesn't work is if the two initial levels are degenerate, because then you have 1 over 0 there and you have to use this equation, but other than that it works universally. The mixed wave functions, psi 1 is going to be a linear combination of the two unperturbed wave functions with coefficients alpha and beta. Psi 2 will be the orthogonal mixture, minus beta phi 1 plus alpha phi 2. I have to have alpha squared plus beta squared equals 1. And this smaller amplitude beta is given also in terms of r by this expression. Okay? And now you can make universal plots. This shows beta, the amplitude of the smaller, as a function of r. And remember, r is the unperturbed spacing over the matrix element. So if the unperturbed spacing is large compared to the matrix element, you're over in this section. I'm having trouble with this. You're over.
Yeah, fading stuff.
Okay, so I'll do that. You have the curve is here, corresponding to small beta, so the mixing amplitudes are very small. If the matrix element is comparable to the unperturbed spacing, so that r would be 1, you're down here, you have a very large mixing amplitude of 0.5. The largest you can have is 0.707. This shows the repulsion of the admixed states, so it's the repulsion, the shift in units of the unperturbed separation, and there are two curves on here just because to blow that up. The upper curve goes with the lower scale, and the lower curve goes with the upper, and so you can just read off this plot for any case you want what the final energies are, what the repulsion is, and since you know the initial levels, you can get the final levels. So this gives you a universal way of getting the final energies for any set of initial energies and matrix element. Okay, clear? Here's a table with some examples. These equations refer to equations in my textbook. Don't worry about that. So here are examples of cases for R, ranging from very almost degenerate levels to levels that are far apart. This is the shift in energy compared to the unperturbed energy. So if they're very close to each other compared to the matrix element, the shift is big. If they're very far apart, the shift is very small. If they're very close together compared to the matrix element, the mixing amplitude is large, and it goes down. Okay? Here I do a specific case where I take 100 kilovolts unperturbed energy separation, and then these R values correspond to these interaction matrix elements. If I have an unperturbed spacing of 100 kilovolts and R is 0.2, it means the matrix element is 500 kilovolts, 100 over 500. And in that case, the shift in energy will be 452 kilovolts. So these levels that are 100 kilovolts apart initially will each move by 452 kilovolts. That's a huge mixing. If I take R1, the wave function amplitude will be 0.53, and the levels will each move 62 kilovolts. If I take an R of 10, the wave function amplitude is 0.1, and each level will move 1 kilovolt. Okay, and you can fill in any other numbers you want here. This gives some nice examples. Okie dokie? All right. Here is a concrete example, which I don't think I'll go through, but it'll be in the slides. I take a case of two levels which are 200 kilovolts apart with a 50 kilovolt matrix element. So that's an R of 4, and that's in between 3 and 5, so you can already guess. But you can actually look at this and guess what beta is going to be. It's going to be somewhere between 0.19 and 0.29, and it works out to be 0.23. And the shift is going to be in between, where is it? The shift will be between 0.04 and 0.1, and it turns out to be 0.059. You can work through this, okay? It's just designed to give you a concrete example where you can actually work it out, okay?
Excuse me.
Yes.
I have a question. That previous slide. This in the case of R equal 0.2 or 0.5, that is very large. Shift is very large.
The shift is very large compared to
Yes. Compared to the
This is a case where the matrix element mixing the states is larger than their separation,
yes.
and they go,
Yes.
okay?
In this case, can we describe this case by perturbation theory?
Well, this is an exact answer because it's just two-state mixing.
Yes.
So this is exact.
Exactly. Not perturbation.
No.
No, I think he has a problem because these formula are derived using perturbation theory,
Yes.
and in
Yeah.
this case, obviously, the interaction is maybe comparable to the
Yeah.
Hamiltonian, the
Yeah,
matrix element Hamiltonian is compared to the
If
interaction.
you diagonalize the matrix, you get this.
Yeah, yeah. I think that this was here for, even though I don't know what to say
Okay.
here.
I want to look at two specific cases. One is degenerate levels. This will turn out to be very important. For degenerate levels, delta E unperturbed is 0, and so R is 0. You can't use the formulas with an R in the denominator, but you go back to the original ones, and you find out that the final energies are the unperturbed energy plus or minus V. That means the final levels are separated by 2 times the matrix element. So they are 2V. And that has a very interesting implication, which is sometimes very useful. 2 levels that mix can never be closer than twice the matrix element. Okay? And in fact, this historically was very important in the study of odd mass nuclei, where the Coriolis interaction is important. There were levels that were found that were isolated 2-state systems that mixed, and they were closer than twice the matrix element. And so that led people to understand you had to attenuate the Coriolis mixing. It has lots of other implications. In this case also, the wave functions are as mixed as they can possibly be because the initial separation is 0, and so beta is just 1 over the square root of 2.707. Okay? Another case which is very useful is weak mixing. That corresponds to R much greater than 1. And if you plug in the formulas, I'm not going to go through this, it's just algebra, you get that beta is 1 over R. Okay? So beta then is simply the matrix element divided by the unperturbed spacing. Okay? And the energy shift is the unperturbed energy shift divided by R squared. Okay? I'll do a couple of examples.
So this is perturbation. Here.
This, yes. So suppose you take R of 10. Okay? These are approximate formulas. Suppose you take R of 10, then this formula would give beta of 0.1, and it would give a separation of 0.01. The exact results, yes, thanks for saying that. The exact results are beta equals 0.0985 instead of 0.1, and this quantity 0.0099 instead of 0.01. So R of 10, these formulas are essentially perfect. Even for R as small as 3, this is where the initial separation is 3 times the matrix element. That corresponds to pretty big mixing. These approximations give you beta of 1 over 3 of 0.33, and the energy is 1 over R squared, 1 over 9, which is 0.11, and the exact values are 0.29 and 0.101. So even for quite large mixing of 0.33 amplitude, these formulas are pretty good. Okay, and so these are very, very useful guidelines to always keep in your mind when you're looking at nuclear levels and their mixing. Now, real nuclei have more than 2 levels, and they mix. Oh, we got plenty of time. Okay. And they often mix with each other. And so then you're typically solving a matrix like this, which you have to diagonalize. And the final wave function will be, just like before, it'll be a sum of amplitudes of all the initial wave functions with different amplitudes. The details will depend on the interactions and on the energies. I want to discuss one important case where all of these levels are degenerate. Now that's not a realistic case, but it contains the essence of a lot of physics we'll discuss. And so I want to, this is what I would call an extreme toy model. If you apply it in a realistic case, you would get answers, like for samarium, you would get answers like 10 to the 14th, whereas the real answer is 200, so it's approximate. But it contains the essence of the physics. So suppose I take n degenerate levels, and suppose each one mixes with all the others equally. So if I have 5 levels, this one would mix with this by interaction V, this with this by V, this with this by V, and so on. They would all mix by matrix element V. What happens? What happens is this. 4 of them go up by an amount V, and of course you have to conserve the total energy. So one of them comes down by n minus 1 V. Okay? This, and the wave function for this level, is all equal amplitudes of all of these basis states just with a normalization factor. This is the essence of collectivity in nuclei. You have a set of states which mix, one state comes down, its wave function is all in phase, and it has the collectivity of the whole system in it. Okay? And you will see this again and again and again. And thinking about this will instantly, as you'll see, help you understand the entire evolution of structure across the nuclear chart. So that's what I just said, absolutely fundamental result, foundation of collectivity. Coherence, collectivity, and the energy lowering all grow with n, goes down as n minus 1, so the more states you have interacting, the lower the collective state will be. And as I said, this largely explains a lot of the general features of the evolution of structure. I want to apply this to a calculation of a transition rate. So let's assume I have n degenerate levels. Okay, we know what the wave function will be. It will be this, where a, this normalization factor, is 1 over the square root of n. And I want to calculate, let's assume there's a ground state which is not mixed, and these are 2+ states. I want to calculate the transition rate from the final 2+ state to this ground state. I'm not sure all of you know this notation. All right, does everybody know what a BE2 is? Anybody not know what a BE2 is? It's no embarrassment. Okay. So a BE2 is the notation we use for the square of a transition matrix element. It's related to the transition rate, but there's some other factors that go into the transition rate or the lifetime. But it's defined as 1 over 2 times the initial spin plus 1 times the square of this reduced matrix element from 2+ to 0+. Okay? I'm going to calculate without the square first. So the matrix element itself, from this 2+ to this, is going to be the matrix element to the 0+ with this mixed wave function there. And so I can write that, since this mixed wave function has this simple form, it's just simply A times the sum over all the individual matrix elements. Is that clear? And now I'm going to make the approximation that all these individual ones are equal. That is, the matrix element for each of these initial unperturbed states to the 0+ is the same. And I'm going to call that, I think I call it, yeah, okay. I call it W. I don't know why I call it W. Okay, so now I take this, each one of these individual ones is W, and so I get that the matrix element is N, because there are N components here, A, W, N, A, W, and when I put in the value for A, 1 over the square root of N, I get that this is the square root of N times W. The BE2 is the square of this. I guess I've dropped a factor of 5, but it doesn't matter. So the BE2 is proportional to N W squared. So that says that the transition rate from this final mixed state is N times the transition rate from any one of these. Okay, or I shouldn't say transition rate, I should say the BE2. So that's an enhancement of n. If n is 5, that's an enhancement of 5. If n is 10 to the 12th, that's an enhancement of 10 to the 12th. And you will see that this is a gross approximation. Gross doesn't begin to describe how gross it is. But the idea that the collectivity of these transitions increases with the number of states that you have to start with persists. Okay, okay? It's a fundamental property of collective states. Okay, so that's a kind of quick introduction to two-state mixing, and now I want to start to look at some of the data. I want to look at nuclear level schemes, how they change with proton and neutron number, what the challenges for theory are, and especially what are the key observables for testing theories. And I'm going to discuss later on, mostly tomorrow, some geometrical models in some detail, and today I will discuss the independent particle model as well. My discussion of the independent particle model will be very simple, and I don't want to say hand-waving, because I use the word hand-waving to mean what you say if you don't know the answer, but it will be, let's say, extremely simplified. Pete, later in the week, will give a much more formal presentation of the independent particle model. And also, we'll both talk about residual interactions. First, to try to describe the data without any understanding of the physics of what's going on is very difficult. So I want to bring in a couple of slides on basic models without deriving them or anything, just sort of like a deus ex machina pulling it out of the sky, just to give you some labels, okay? Okay, first of all, what observables will we look at? When you study nuclei, you have to measure something. There are a lot of things you can measure. These are not all of them by any means, but they're the ones that I will talk about most. Masses are one thing, and we will find that we can learn a lot about nuclei from their masses. We already learned that the nuclear force is short range and attractive. We will find out later on we can go much, much further. All nuclei have a ground state, which is good. They have excited states, and these are just, it's not a real nucleus, it's just a random example. Almost always, I'm talking about even nuclei. I will discuss, in the third week, I'll discuss odd mass nuclei. Almost always, I would say 99% of the time, the first excited state is 2+, and probably about 97% of the time, the second excited state is 4+, and then you have other states. Okay? So we will look at these states, their spin imparities and their energies. One important measure of structure, which does not tell you everything, but it's a good first guide, is this quantity R42, which is the ratio of the 4+ energy over the 2+ energy. So in this case, it's 2.5. Okay? I stress that whenever I look at an even nucleus and ask myself what's going on, that's the first quantity I look at. But it's very important to understand it doesn't tell you everything. Okay. Very important also are BE2 values, basically transition rates from these various states. Okay. Typical notation is the thicker the arrow, the bigger the BE2 value. That's a common practice. Okay, so these are the observables, most of the observables we'll look at. Okay, now the idealized models. They're basically two classes. There's the independent particle model, which is just a model of nucleons running around the nucleus in orbits. And that's the foundation of sort of nucleon-based picture of the nucleus, the shell model, if you want. And I will go into some detail on that. And then there are collective models, where this model becomes impractical. You resort to collective models. Remember the very first slide I talked about a microscopic and macroscopic approach, one looking at nucleons and their interactions. This is the simplest version of that, I mean utterly simple. And then I talked about a macroscopic picture where you look at what the many-body system as a whole is doing with its own quantum numbers. That's collective models. And I'm going to talk about two collective models right now, very, very briefly. A harmonic vibrator, and what you should picture in your mind there is a spherical nucleus that can vibrate. Okay, and that's all I'm going to say about it basically for now. The other simple model is a deformed rotor. What I mean by that is a nucleus that's shaped like, and I'm sorry to have to get patriotic about this, like an American football. All of you know what an American football looks like? Anybody not? Okay, so looks roughly like an American football. And since it's non-spherical, it can rotate. It can also vibrate, and so you get both of those kinds of excitations superimposed on top of each other. These two are collective models. They involve things going on in the nucleus as a whole, and this is a nucleon-based depiction. Okay. So some spherical nuclei are quite rigid, but many of them are soft. Soft means that they can oscillate a little bit. Later we'll talk about this in terms of a potential, where you have a potential, the nucleus can oscillate back and forth, but right now I want to be very qualitative. They can be soft to vibrational motions. The lowest such excitation is a quadrupole excitation, so that's an excitation where you take a sphere and then it looks a little bit like the American football this way, and then looks like it this way, and it goes back and forth. That has 2 units of angular momentum, and so the first excited state will be a 2+ state. Now, there's no reason why you can't have 2 of these excitations superimposed on each other, and so if you superpose 2 of these quadrupole spin 2 excitations, which can be called phonons, you get a 4+ state, and since you're just superposing 2 of the same thing, the energy of the 4+ state is twice the energy of the 2+ state. And that's a 2-phonon state. There are others 2-phonon states which we'll talk about, but for now, just look at this, and clearly R42 is 2.0. So, just bear this in mind. I will use this kind of language to talk about some of the nuclei we'll see. Okay. The other is, nuclei are 3-dimensional. That means they can rotate. And rotational energies in nuclei. So I'm picturing now, just to make it very clear in case some of you are confused, here I have a roughly an American football shaped nucleus. It's not exactly. By rotation I do not mean this. I mean this. Okay, a quantum mechanical object can't rotate about a symmetry axis. So it's a rotation like this or like this. And I've got to orient this back to right? Okay. Those energies follow the energies for the quantum mechanical symmetric top, which means that the energies of these rotational states go as h-bar squared over 2 times the moment of inertia times j plus 1. Comment here that I should have made before. I use the letter small j to mean the angular momentum of a nucleon, and large j to mean the angular momentum of the nucleus. Okay, sometimes in the literature you will see a large I. Typically, but not always, people who use large I are or have been interested in high spin states, and those who use J tend to have been interested in low spin states. That's not a rule, but it's common. And now I want to use this simple formula and just get one result very quickly. Suppose I put angular momentum 0 in here. Can anyone tell me what this is equal to? There's a hint here. Everybody see that?
Yeah.
Okay, suppose I put angular momentum 2. Well, it's going to be proportional. I don't care about that. 2 times 3. Can anyone do that without a calculator? No? Somebody want to tell me? 6, good. And now a little more complicated, 4 times 5. Yeah. What?
20.
I thought you said 7. 20, okay. So the 2 plus should be in an energy. Sorry? What?
It's of the order of magnitude 7.
Yeah, okay. We'll see later that those differences tell us something. Okay. So the 2 plus state will be at an energy proportional to 6 and the 4 plus 20. Now it gets a little tougher. The 4 to 2 energy ratio is 20 over 6. Can anybody guess what that could be? Okay, 3.33. All right, so that's a very simple result for a rotational excitation. And here's one example. There's this formula again. This is nobelium 254, and here you see this rotational band. And what I do here, you'll see this more later, I normalize this 2 plus, this is the formula. I normalize this 2 plus to this energy. In other words, I use this excitation energy to establish what h bar squared over 2I was. And then I calculated these levels. And you'll see they agree very, very well with the data. You'll also see that they disagree slightly. This A plus is a little higher. We'll understand that very soon. Okie dokie? All right. So that's, well, this isn't doing anything, so. Okay, so now I want to look at the empirical evolution of structure, and this is a good place to stop, so let's have a coffee break. Be back here at 11, and we'll look at what real nuclei are doing.